Now that we have the product rule and the quotient rule as part of our repertoire, we can tackle derivatives such as the derivative of tangent, the derivative of cotangent, the derivative of secant, and the derivative of cosecant. I'll show you why we can do that. It's because I can rewrite tangent, which I don't know the derivative of right now, as sine x over cos x. We know that's what tangent is equivalent to. And then we can take the derivative of sine over cosine by using the quotient rule. And let's see what we get. Derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Now, it's important to note that cosine of x squared can also be written as cos squared of x. These are equivalent. Okay, so make sure we know that the square being over the cosine means you're just taking the cosine of the value and then squaring it. So I can really write this, just to simplify, as cos squared x plus sine squared x over cos squared x. Well, we should recall kind of the standard trig identity coming from the Pythagorean theorem, a squared plus b squared equals c squared. Well, in a unit circle, your horizontals and your verticals of your right triangles all have an hypotenuse of 1, so horizontal squared plus vertical squared is going to equal 1. So turns out the derivative of tangent is 1 over cosine squared of x. Well, 1 over cosine is the same as secant. So it turns out the derivative of tangent is secant squared of x. Just for fun, go ahead and do that same kind of procedure to figure out the derivative of cotangent. So I'd write cotangent as cosine over sine, and then I would go from there. I end up with negative sine squared minus cosine squared over sine squared. I can pull out a negative 1 here and make both of these positives and use that same identity, sine squared plus cosine squared is equal to 1, to get our derivative of cotangent being negative 1 over sine squared. Well, that can be written as negative cosecant squared. Okay. Now, in the future, you are not going to have to do this derivation to find these derivatives. However, you will have to commit these to memory, along with the derivatives of secant and cosecant. We're not going to do the derivation, however, we could. The derivative of secant ends up being secant x times tangent x. The derivative of cosecant ends up being negative cosecant x cotangent x. So these four are combined with your already known derivatives of sine and cosine. Derivative of sine is cosine. And the derivative of cosine is negative sine. You must commit these to your memory. You must have them memorized. Some ways to help you memorize them. Whenever you see your trig function that starts with a c, the derivative is always negative. Also, you kind of see how tangent and cotangent derivatives are very similar, and secant and cosecant derivatives are very similar. So however you want to get those memorized, you will need to know their derivatives in the future. It's important to note this is not secant of tangent of x. You cannot write secant x tangent x as secant tangent x. This would be incorrect. It is a product of secant x times tangent x. Okay, some people make that mistake. All right, well, now we have more tools to be able to tackle some things like finding derivatives at certain values. We can even write equations of tangent lines if we wanted to. But let's find the slope of the tangent of x minus tan x. It's just taking the derivative, but now we'd have to evaluate our derivative that would be kind of a little bit more complicated in terms of its trig function at the point, at the x value. So I start with the derivative here. I have 1 minus secant squared x. It's just the derivative of x minus the derivative of tangent. And I need to find that at pi over 4. Now, some people are a little bit confused when tackling something like this. Okay. Remember, just like I told you with cosine, this could be written as the secant of pi over 4 all being squared. These are equivalents. That's how we deal with that square. And then you can find the secant of pi over 4. Secant is just 1 over cosine. You know what the cosine of pi over 4, so we can find the secant of pi over 4 and then square it. So let's do that. I'll have 1 minus 1 over cosine pi over 4. Cosine of pi over 4 is root 2 over 2. So 1 over root 2 over 2 becomes 2 over root 2. Now you can either rationalize this first or just square it. Square the top and the bottom. Don't just square the top when we're squaring things. If I square the top, I get 4. Square the bottom, I get 2. So this is 4 halves, which is just 2. I have 1 minus 2, which is negative 1. Okay? So turns out the slope of the tangent to x minus tan x, we don't even know what x minus tan x looks like, but you could say, hey, the slope of the tangent or the instantaneous rate of change of the function is negative 1. All right, you guys do x secant x. Find the derivative of that at pi over 4. And then check your answers with a neighbor. probably have like y prime of pi over 4 here. Now let's make sure we recognize that that is a product. We should be using the product rule. And that is our correct derivative. Make sure your derivative is correct. It should be secant x plus secant x tangent x times x. We know the secant of pi over 4 is 2 over root 2. We found that out earlier. So let's go y prime of pi over 4 is equal to 2 over root 2 plus 2 over root 2. Tangent of pi over 4 is just 1. And then I have a pi over 4 here. So I end up with this funky looking derivative. However, it is the correct tangent slope. 2 over root 2 plus 2 pi over 4 root 2. This could be simplified to pi over 2 root 2. I could give it a common denominator, and I could simplify that. When would we need to simplify this? If we have a multiple choice question and we don't see this answer, we would have to simplify it. Probably, if you have a question like this and you see an answer like that, usually they would only have an answer that would be one term, so they would be combining those two terms. This is a good example of if you end up with this answer and you don't see this answer on your multiple choice answers, it doesn't mean you did something wrong. Okay, a lot of people, they get to an answer, they don't see that answer, they think they did something wrong, and then they just guess, or they just skip the problem, or they think they're doing something wrong, and they lose a lot of confidence. When you stop here and you don't see this, have faith in what you've done and just try to simplify. So I would then probably write this as pi over 2 root 2. I would multiply the top and bottom of this by 2, so that it would be 4 plus pi over 2 root 2. Maybe you'll have a radical and a denominator in your answer choices. I've seen that before. I've seen situations where we've had to rationalize. You have to be prepared for everything on the AP exam. If you were to rationalize this, you'd multiply the top and bottom by root 2. You'd get 4 root 2, or maybe root 2 times 4 plus pi over root 2 times root 2 is 2 times 2 is 4. Okay, maybe that's it. I don't know. Okay, now that we found the slope, we can easily write equations of tangent lines. So maybe instead of finding the derivative, we can find the equation of the tangent line. And let's just write the equation of the tangent line for this guy at pi over 4. All we would need is the function value y at pi over 4, which would be pi over 4 minus 1. It's a funny looking function value, however, probably can't simplify this anymore. And what we would do is use that and our tangent slope. Come on. There we go. We'd use that and our tangent slope, which was y prime at pi over 4, to write our equation. Y minus pi over 4 minus 1 is equal to my tangent slope, which was just simply negative 1, x minus pi over 4. Okay, and here we have an equation of a tangent line to x minus tangent of x. We need to be comfortable with equations of lines that look a little bit funky. On your quiz today, you had a funky looking tangent line on your last question. Okay, the slope was weird. It was like 4 over 9 pi squared or something like that. I'm not sure, but you have to be comfortable with that. Hopefully we did that correctly. We didn't panic when we got our answer. I don't know exactly what the answer was. Maybe you guys remember. What was it? Was it 4 over 9 pi squared? That was it. All right. Okay, good. All right, let's talk about higher order derivatives. So we know that if I have some y, which is equal to some function, and I take the derivative of it, I say that either using kind of multiplication, the derivative of y we can say is dy over dx. You can write that as y prime, however, I'll just say that the derivative of f is f prime, so that's kind of similar. Well, we can take derivatives of derivatives. Let's see what happens if I took the derivative of this derivative. I'll call this my first derivative. Well, the notation on the left is really the more confusing notation, which is why we write this. If I took the derivative of dy dx, think about multiplication. The d gets multiplied by the dy, so really it'd just be d times d squared y. And then the dx times the dx would be dx quantity squared. So we got d squared y over dx. Now, you should be using parentheses here. However, in your book and on questions, they won't have it in parentheses. They'll just have d squared y over dx squared. So this would be the second derivative notation of y, dx squared. And you just put another tick mark next to f, or y prime. We call this our second derivative. Now, moving past that, sometimes you'll have 3 tick marks. Sometimes after 2 tick marks, they just start using numbers. And we could have just a third derivative, or what we'll call is an nth derivative. So if I see notation like this, we'll start using numbers. So like f3 or f4 of x, this would be the third derivative or the fourth derivative. This we'll say is our nth derivative. Okay, just in this kind of form. Now, how do we take second derivatives, third derivatives, nth derivatives? You're just going to take derivatives of derivatives. There's no fancy way to do this. So I could ask you a question. If f of x is sine x, what is the fourth derivative of sine x? Go ahead and do that. All you'd have to do is take the derivative, and then take the derivative again, and then take the derivative again, until you get to the fourth derivative. Check your answer with a neighbor. What is the fourth derivative of sine? Go ahead and do it. It won't hurt you. Just take the derivative, and then take the derivative again, and then take the derivative again. What do we get? Sine is correct. My first derivative is cosine. My second derivative would be negative sine. My third derivative, you can either do 3 tick marks or the 3, would be negative cosine. And then my fourth derivative would be positive sine. So we're kind of back to where we start after 4 derivatives. We're back to sine. So we can use that knowledge to find the 86th derivative of sine. Go. discuss with your neighbor.
What real-world jobs involve derivative of fourth derivative? Sorry.
Usually you won't be doing fourth derivatives. Usually second derivatives are kind of where we stop, because second derivative tells us something about our original function. But these are just interesting situations.
So most jobs don't usually use this?
Well, they use second derivatives. Okay.
I'm looking to get a biomedical engineering degree, maybe.
Second derivative is very important. It's all about acceleration. How quickly is something moving up or down? All right, what do we get? Nice, 86 mod 4. No, I love it. We know that the 84th derivative is sine, right? Just take two more derivatives. Derivative of sine is cosine, derivative of cosine, negative sine. Okay? Simple, right? Well, you guys can also find the sixth derivative of 2x to the fourth. Go ahead and do that. Check your answer with the neighbor. We should get 0 if we have a positive integer, if we have a natural number as our power. Eventually, our derivative will be 0, and it'll continue to be 0. If I asked you for the 50th derivative, you'd say it's 0. The 80th derivative, it's still 0. However, if this power was a fractional power, then we would actually have to continue to take the derivative that will not equal 0. It'd end up going into the negative powers. If this was a negative power to start with, it would just get larger in the negative direction in terms of our powers, okay? Only in this situation do we have these derivatives that end up equaling 0. Now, when do we use these like second, third, fourth derivatives? Well, usually we'll just stop at the second. The second derivative will tell us stuff about our original function. So we will kind of, next unit, get into what the second derivative can tell us about the original function. So let's just find the second derivative here, just as practice. This is a quotient. So you're going to have to use the quotient rule twice. And probably after the first time you use the quotient rule, you probably should simplify so that the second time you took the derivative, it would be of the easiest function that you could have. As of right now, you don't know how to take the derivative of x minus 1 squared. So for today, you would have to distribute that to be able to use the quotient rule. In the future, though, we'll learn how to take the derivative of that. All right, so I got my first derivative, -1 over x squared minus 2x plus 1. I now have to take the derivative of that to get the second derivative. Derivative of the top is just 0, so that's nice. This stuff will just go away. Minus the derivative of the bottom I can do times the top. That would just make this a plus all over the bottom squared. Okay, that's my second derivative. Nothing fancy, nothing special, just derivatives of derivatives, okay? Here comes an example of why we need a second derivative. For our straight line motion problems, let's think about things. I have a position function, x of t, and I want to find the acceleration of the object when its velocity first equals 0. Great problem showing off using second derivatives. Why is this problem using second derivatives? Can anybody answer that? Yes, because the derivative of velocity is acceleration, and the derivative of position is velocity, so the second derivative of position ends up giving you acceleration. Let's work our way through that. X prime is v. If we do that, the derivative of x here is -3t squared plus 12. Well, if I take the derivative again, I get x double prime, which is the same as v prime, which gives us a. The instantaneous rate of change of velocity gives us acceleration, meters per second squared. This ends up being -6t, okay? So now I have my velocity function and I have my acceleration function. I need to find the acceleration when its velocity first equals 0. So what am I going to do? Set my velocity function equal to 0, solve, find t, plug it into a. All right, go ahead and do that real quick. Now we know the second derivative of position gives us velocity. I don't think I specified in your quiz, but usually we say for these problems that time is just going to be positive. So I'd be looking just for this positive answer, 2, and then we'd find a of 2. If you just put positive and negative for one of your answers for time, it's fine. Don't worry about it. That's it. A of 2 is -6 times 2, which is 12. -12. This would be whatever position, meters per time, whatever the time is, second squared. Okay, second derivatives, straight line motion. This is a problem that you might see. It doesn't usually trip students up, but it might. You start with the second derivative. You're asked to find the fourth derivative. Just take the derivative 2 more times and you get the fourth derivative. It's nothing fancy. So we can do that really quick if you want to write this down, just so that you're comfortable with it. So this is x to the 1/2. So this would be x to the -1/2. I'm not even going to simplify, because if I did, I'd just have to use like the quotient rule possibly. That's it. That's our fourth derivative. Just take the derivative 2 more times. Okay, that's higher order derivatives. All right, so we got the derivatives of some other trig functions, and then we have some higher order derivatives. Now we're going to get into tricky problems that always show up on the AP exam They're called table problems. And we will be given information, whether the information is in a table or the information could be given to us in a graph. And then we are not given an expression for f of x or g of x. Instead, we just have questions like this and this. So write down those questions. This being our first question that we are going to conquer, and this being our second. The first one that we do on the left is actually a really easy one, and it actually is not a good one to think of when we're doing our other table problems. And the key to all these problems is just to know your rules. Okay? So if you're asked this question, what's the derivative of f plus g at x equals 2? Well, you'd find the derivative of f plus g just saying that the derivative of f is f prime and the derivative of g is g prime. Since we're adding, we can do that. The derivative is just f prime plus g prime. Well, now this is just at x equals 2, so I'd be plugging in 2 everywhere. I'll plug in a 2 here and a 2 here. Right? Simple. Well, in our table, we can find f prime of 2. Here's f prime when x is 2, I get 7. Here's g prime of 2, negative 4. And that's how we get the information from our table to get our answer. It's a numerical answer. Sometimes we can simplify it like this. Sometimes we'll have pi's and we can't simplify it. Okay? But that kind of sets us up for some issues when we tackle something like this. Because a lot of people, when they see something like this and they say, oh, find the derivative, they say the derivative is 3f prime g prime. Right? You just take the derivatives of all the pieces. Is that correct? No, this is definitely not correct. Because you know that we have a product. And when you have a product, you must use the product rule. This is why you need to know your rules. You need to be comfortable with sometimes this being 3g of x times f of x. Maybe in an order that is not familiar with you and might be designed to confuse you. Now the 3 sometimes messes people up as well. Let's talk about the 2 ways we can deal with the 3. We know a rule where we have the derivative of a constant times a function, just leave the constant out to the side and then multiply by the derivative of the function. We could do that with the 3. We can, what I say, leave it out. And I can say it's 3 times the derivative of f times g, which is f prime g plus g prime f. Or we can lump the 3 in. What do I mean by lumping it in? I mean, take the 3 and put it with the f of x. Let's use red for that. And multiply that by the g of x. You'd still be using this rule. It would just be kind of in multiple locations. So let's see. I would take the derivative of 3f of x would be 3f prime of x times g of x plus the derivative of g of x, g prime of x, times 3f of x. So all of a sudden, it's just the 3 ends up getting naturally distributed when you use the product rule and you lump the 3 in. It's up to you how you want to deal with it. Sometimes I like to leave the 3 out, the constant out. Sometimes I lump it in, depending on the situation. Usually I'm a lumper. Okay, now you guys practice getting the information off of your table and finding this value at x equals 4. like my room's going to flood. Do you hear that water running? Yeah, no, I don't have a fish. Sometimes I don't know what's going on back there. I don't have a key to that.
Just wait here till maintenance comes by and find out.
Well, like, I'll have to call them. So either way, you'll get the right answer. F prime of 4 is pi over 2. G of 4 is -3. G prime of 4 is pi times 3. F of 4 is 9. So I get -9 pi over 2s plus 27 pi's. Uh, 27 pi's. That's 54 pi's. 54 minus 9 is 45. So this would be 45 pi over 2s. All right, your turn. Now I'm going to give you a quotient, and I'm going to try to trick you. So we'll just do this one on the left. We have, let me give you a number as well. 2 g of x over f of x at x equals 9. Why don't we change g prime from a pi to just a number, -2. Make it -1. Okay. Go. Tackle that yourself. Notice what the problem is designing to do. It's trying to trick you by putting g where we're used to having f, and by putting f where we're used to having g. So you got to kind of get away from maybe f's and g's and maybe think about tops and bottoms. Or if you wanted to, you can, kind of, it might confuse you, but write a little f or a little g there. Now you can either lump in the 2 or you can leave the 2 out. It's up to you. Probably in this situation, I would lump in. Check your answer with a neighbor, and let's see what we get. Everybody get 1/4? Yeah? All right, good. That's the answer. Let's make sure we get 1/4 if we haven't gotten it. Is our derivative correct? Lumping in the 2, I have 2g prime times f minus f prime times 2g of x divided by the bottom f of x squared. Then plugging in the values, I have 2 times -1 times 4 minus -3 times 2 times 2 over 4 squared. Okay, so those are examples of given a table. Can we answer that? Sometimes they won't even give you a table. Sometimes they'll literally just have a bunch of stuff in the question saying f of 9 is 3 and f prime of 9 is -2 and f g prime, like they'll just give it to you listed this way. You just grab the information from there. Sometimes, and these are the fun ones, you are given a graph and you need to get the information from a graph. Sometimes the graph will just have line segments like this. Typically it'll have line segments like this, okay? So let's see, it's the same type of problem. You'll have this on your homework. This is P and it equals F times G, and I want to find P prime of 4. So this is a simple question because there's no other constants in front of things. It's just the application of the product rule in a way that you are comfortable with and familiar with. So this is P, let's find P prime of X to start. Well, make sure we're just comfortable with the product rule. So everybody write down this product rule. And now the question is, how do we get information that we're looking for off of a graph? I want you and your neighbors to figure out what f prime of 4 is and what g of 4 is looking at this information. Go. Let's see if we can get some people who can figure this out. The question is, what are the values? What are the values for f prime of 4, g of 4, g prime of 4, f of 4? What are the values? The answer is a number. You know, it's like a number times a number plus a number times a number. What are those numbers? How do you get them off of the graph? Discuss. Did we figure it out? Yeah? What do you think, Mr. Clayton? So -3. Well, how'd you get f prime of 4? The slope of the tangent of f at 4, right? Well, it's just a line segment. What is the easiest way to find the slope of a line segment, like this line segment here? Yeah, rise over run, right? So on this line segment, I go down 1 over 1. The slope of this line segment everywhere is -1. So the slopes of the tangents of this line segment is going to be -1. And then how do I find g of 4, Mr. Clayton?
It's constant. It's just where
Yeah, it's just the function value, the y value, which is right here, which corresponds with this y value of 3. So g prime of 4, this line segment is horizontal, its slope is 0. All of the tangent slopes on this segment will be 0. And then f of 4 is our function value up here, which corresponds with a y value of 7. You end up with just -3 because of that 0. Not that bad, right? You just got to understand, what does f prime mean? Slope of the tangent. Derivative, it's the instantaneous rate of change, okay? Well, let's go ahead and tackle this one, and let's see if we can all get the correct answer. Q prime of 8 If q is f over 2, we have a constant in the denominator. You could take it out. If you took it out, it would be 1/2 times the derivative of f over g, okay? So that is how you could take out, or you can lump in with the denominator. It's up to you how you want to tackle that. A lot of 2's. Make sure you check your answer. Make sure we're getting the same answer. I got 7/8. Did you guys get 7/8? Yeah. Everybody leave the constant out. Ends up for easier calculations. You don't have as many 2's that you multiply. You just have f prime g minus g prime f over g squared, all times 1/2. It would be a lot easier than having all of these 2's. Not a lot easier. It's not that bad. Any questions on this? Getting the 7/8. G of 8 is 2. G prime of 8 is -1/2. F of 8 is 6. F prime of 8 is 2. 2 times 2 times 2. 2 times -1/2 times 6 over 2 times 2 squared. This is the lumped in method. If you had the 2 lumped out, it would be it'd be good. All right, that's all I got. Enjoy the next 4 minutes.